Hi, and welcome to a lecture on 180-degree hybrids and rat races. A 180-degree hybrid is really a mathematical description of the way certain four-port RF devices can be made to operate. So here's the picture you should have in mind. Here is a four-port device with ports numbered 1, 2, 3, and 4. For a 180-degree hybrid, port 1 is often referred to as the sum port, so we use the Greek letter capital sigma. Port 4 is often referred to as the difference port. We use the Greek letter capital delta. And then the signals at ports 2 and 3 are separated by a 180-degree phase shift. And for the purposes of this video, we will assume that everything is lossless just to simplify the description. Now, what it means to be a 180-degree hybrid is most easily described in terms of the S parameters. So here we have 4 ports, therefore we have 4-port S parameters. The S parameters are a 4x4 matrix. The particular S parameters we get for a 180-degree hybrid is given by this matrix. The first thing to note about this matrix is that S11, S22, and S33, and S44 is all 0. That means we have no reflections on the ports. But be careful, this is only true if all the ports are properly terminated. So if all the ports have been terminated into the proper impedance, namely Z0, then all 4 S parameters, S11, S22, S33, and S44, are all 0, no reflections. Next, we consider the S parameters S41, S32, S23, and S14. And those 4 parameters lie here along this diagonal of the S parameter matrix. And for the 180-degree hybrid, they're all 0. What this means is that we have perfect isolation between ports on the same side. So for example, between ports 1 and 4, we have perfect isolation, and between ports 2 and 3, we have perfect isolation. So we can anticipate that we will have some nice characteristics for combining in particular. Next, consider the S parameters S21 and S31. Those lie here and here in the matrix. Now, what these 2 parameters describe is the performance of this thing as a lossless in-phase divider. In other words, if port 1 is the input and ports 2 and 3 are the outputs, then we have a divider which is dividing in phase. In other words, the outputs are in phase. And since we've already identified that ports 2 and 3 have perfect isolation, this will be a very nice divider. Next, we consider the S parameters S12 and S13. Those lie here in the S parameter matrix, and we see that those 2 S parameters are in phase. So in fact, here we have a perfect in-phase combiner. That is, ports 2 and 3 being inputs, and treating port 1 as the output, we see that the signals at ports 2 and 3 will be combined in phase. Next, we consider the S parameters S24 and S34. Those 2 S parameters lie here in the S parameter matrix. In this case, we see that we have a divider, specifically port 4 being the input, and ports 2 and 3 being the outputs. But in this case, the S parameters are 180 degrees out of phase. One is plus J, the other is minus J. So in this case, we have a lossless 180-degree divider, and hence the name 180-degree hybrid. So if you ever have an application where you would like to apply a signal and then have 2 versions of it, 180 degrees out of phase, this would do that job. And in fact, there are many applications in RF engineering where we would like to do exactly that. Finally, we consider the S parameters S42 and S43. Those S parameters lie here in the matrix. Here we see that once again, those parameters are 180 degrees out of phase. What we evidently have here is a perfect 180 degree combiner. That is, ports 2 and 3 are the inputs, port 4 is the output, and what appears at port 4 is port 2 and port 3, but with a 180 degree phase shift applied before that addition. Now, before we move on, be careful. All of this stuff presumes that all ports are actually terminated into the correct impedance Z0. If that's not true, all bets are off. So let's talk about the two applications which give this 4-port thing the name 180 degree hybrid. Those two applications are, of course, the divider application and the combiner application. Let's consider the divider application first. Here I'm showing port 1 isolated. Here I'm showing the input on port 4 and the outputs on port 2 and 3. And we know in that case, from the S parameter matrix, we're going to see a 90 degree phase shift going from port 4 to port 2. And we're going to see a minus 90 degree phase shift going from port 4 to port 3. So here we see plus 90 degrees. Here we see minus 90 degrees. Another way to think of that, of course, is that relative to port 3, port 2 is 180 degrees. So you can think of this as being 0 and 180 degrees. That would be typically the way it's labeled on a device, but it could be either way. Now you can do precisely the same thing with 1 as the input and port 4 terminated as shown here. And in that case, it would not be a 180 degree divider. It would be a 0 degree or in phase divider. In other words, in order to get this 180 degree phase shift between outputs, you must apply the signal to port 4. And also let me note that this impedance hanging off of port 1 is of course important, and also it's going to get no power. It gets no power because, as we identified earlier, there is perfect isolation between ports on the same side. So perfect isolation between ports 1 and 4. Next, let me point out that you can also do both of these things. In other words, you can simultaneously do what we're showing above, that is, port 4 being split between ports 2 and 3 with a 180 degree phase shift, and at the same time, you could apply a signal to port 1, have that end up at ports 2 and 3, in this case with 0 degree phase shifts. You could do both of those operations at the same time, and there are cases in which you might be interested in such an operation. So, to summarize, you can drive port 1 by itself with port 4 terminated. You can drive port 4 with port 1 terminated, in either case with perfect isolation, or you can do both at the same time. Now the 180 degree combiner application. So here's one of the two possible cases shown here. Here the inputs are on port 2 and port 3. We're taking the output at port 4, and port 1 is being terminated into Z0. So in this case, the signal going from port 2 to port 4 gets a plus 90. The signal going from port 3 to port 4 gets a minus 90. So what appears at the output port, port 4, is the difference between these two signals. You can think of this as the subtraction of signals between ports. And this is something which itself has many applications. You can do the same thing with port 4 terminated and port 1 as the output. In that case, you get the addition of ports 2 and 3. That's why we sometimes hang the sigma symbol off of port 1. And of course, you can do both. So you can do the operation I'm showing in the figure above, where we get the difference between ports 2 and 3 at port 4. Or you can do the operation I just alluded to, which is getting the difference between ports 2 and 3 at port 1. And you can do both of these at the same time. One reason these hybrids are so popular is because they are easy to implement, and there are a number of ways in which you can implement them. A particularly easy and common implementation is something called a ring hybrid, which also goes by the name of rat race. So here is the implementation of a rat race in MicroStrip. We see here port 1, the sum port. We see port 4, the difference port. And then ports 2 and 3 are here. And they are connected together by this ring. And this ring has 4 exits. Port 2 and port 1 are separated by a quarter wavelength. Port 1 and port 3 are separated by a quarter wavelength. Port 3 and port 4 are separated by a quarter wavelength. And then we have this remaining section around here, which is 3/4 of a wavelength. 3 lambda divided by 4. In the MicroStrip implementation, all the characteristic impedances shown here are Z0, except for this semicircular section here, which has a higher impedance equal to square root of 2 times Z0. And since it's a higher impedance, it's higher by a factor of 1.41 or so, it's going to be narrower. So this one section, which is semicircular here, is a little bit narrower, and all the rest of the sections have the same width. Now, before I continue here, you should be advised that there are many variants of this structure. So you could see any number of modifications to this basic idea to achieve particular other goals, but the starting point is usually this thing. Now, a couple things to note here. First of all, this particular structure, the rat race, is narrowband. And it's narrowband because it's only perfect at one frequency, namely the one at which the line lengths are either lambda by 4 or 3 lambda by 4. At any other frequency where this is not true, this will not be exactly a 180-degree hybrid. Secondly, you can probably see some similarities here to the Wilkinson device, and also to branch line couplers, which are quadrature hybrids, not 180-degree hybrids. The branch line coupler is also a ring, if you'd like to think of it that way, a ring in which the ports are separated by a quarter wavelength in all cases for the branch line coupler. Also, you should probably be asking the question, how do we know that this gives us the S-parameter matrix of a 180-degree hybrid? I started this lecture with a mathematical description of the way a particular 4-port behaves, and I called that the 180-degree hybrid. It is not obvious at first glance that the rat race will give you the same S parameters. In order to verify that, the thing to do is even-odd mode analysis. It's not very complicated to do. It is a little bit tedious, but any good textbook will explain it and kind of walk you through the proper procedure for analyzing this thing, which will then show you that, in fact, for the rat race, you get the parameters that describe a 180-degree hybrid. And I'll also warn you at this point that there are a number of descriptions that you can come across online, in certain application notes, in informal conversations sometimes, where the description might not be completely right. The only way I know to properly analyze this thing is even and odd mode analysis. Let me finish up here by giving you 2 other ways that you can implement a 180-degree hybrid. The rat race is one. Another one is something called a tapered coupled line hybrid, which is sometimes seen in MicroStrip. Yet another way is a thing called the magic T. Magic T is a type of waveguide junction. So if you're using waveguides, perhaps you're at a very, very high frequency regime, then the magic T, a particular way to join waveguides together, will give you the S parameters that describe a 180-degree hybrid. And all those features I showed you at the beginning of the lecture would apply to the magic T as well. That concludes this talk on the 180-degree hybrid and the rat race.